Hi class, in this video we're going to kind of just give an introduction or set the stage for Math 105. And so it's my hope that in this class that it's really unlike any other math class you've had. So what we're going to start to do here is think about mathematics not just in terms of the content, so that's like taking, say, a standard addition problem and working out the correct answer, but starting to think about what are the models? How can we show the addition that's happening? How can we talk about the joining of two sets of quantities to get a total number? Or how, once we get to negative numbers, can we start to use chips to show that when we take away a -3, why is it that the end result is the same as adding 3? So what is happening behind the scenes in terms of the concepts or the big idea of mathematics that causes the algorithms that we often have, these processes, these 1, 2, 3, 4-step procedures, to give us the correct answer? And so we're going to really start to think about that in a different way. And so these first couple days, these first couple videos, we're going to be looking at problem solving generally. We're going to be looking at kind of visual problem solving, and then we're going to look at some patterns. And so really kind of pushing us to think differently about what mathematics can be. And so this really is an attempt to set the stage for this course. And something that I want to start with is ways we are all smart at mathematics. And so take a minute to look at some of these ways that we can be smart at math. We can be smart at mathematics if we try and try and try again, if we persevere, if we don't give up right away. We can be smart at math if we're good at drawing pictures that represent the mathematics that's happening. Maybe we're really good at working with manipulatives, and that's another way that we can be good at mathematics. Or maybe we're really good at putting our mathematical thinking into words, and so being able to talk and write about our mathematics is a way that we can be smart at mathematics. And so here's a longer list, and you might want to take a minute to look through this. If you need to, pause the video, but find a way that you are smart at mathematics. And I promise that every single one of you will find at least one, if not many ways, that you're smart at mathematics. And this really is a new way to start to think about what does it mean to be smart at mathematics. And then after you do that, I want you to think about what things aren't on this list. Were there things you were looking for, or were there things that you've heard people say that make them smart at math that weren't on this list? Because there are two things that I purposefully don't have on this list. The first is I can get the correct answer. Because rarely is it the correct answer that's the most interesting part of the mathematics. Mathematics is about problem solving, and problem solving with quantities. And so mathematics really is more about the process. How do we get from the things we know to some sort of answer? Than it is just that answer alone. And then the second thing is how quickly someone gets to an answer. I get the right answer quickly isn't on this list. Because there's this really great article that I love that's called Smarter Isn't Faster. And so really starting to think about, maybe in elementary school you had those time tests where you had to get your multiplication facts done really quickly. And maybe even mentioning those like raises a level anxiety in each of you. And so thinking about smarter isn't a measure, or faster isn't a measure of intelligence. And so really what I want us to be thinking about is we're smart at math when we can put our thoughts into words, when we are persistent and we don't give up when we can't figure it out, when we're able to take a complicated problem and break it down, when we can draw a picture or work with manipulatives to represent the problem. Those are ways that we can be smart at mathematics. And just as all of us have some ways that we're smart at math, none of us are smart at math in all of these ways. And so that's why really when we think about how kids learn mathematics, it's important that kids are learning mathematics in groups. Now, teaching online isn't the most conducive to working in groups and being a community. But the beauty of working in small groups is that each of us have ways that we're smart at math, and often they're different than ways that other people are smart at math. And so when we work together, really we complement each other in the ways that we're smart at mathematics, and we're more successful, we're smarter together, which is actually the name of a book. Smarter together when we work in groups in mathematics. And so I want to start with an activity that's probably going to look like something you've never done in terms of fractions. And this comes from Jo Boaler's book, Mindset Mathematics. And this is actually, she's a researcher out of Stanford, and she does a lot on mathematical mindsets. So it's thinking, it's not that someone is or isn't a math person, but rather we all learn mathematics, right? Nobody is born with all of this mathematical knowledge. And it's important that we realize it's not that I can't do something in math, it's just that I don't know how to do it yet, or I don't have all of the tools I need to do it yet. But that yet is really the key word there. And so this is a 4th grade task, but I promise it'll take us a little bit of thought. So first we'll start with these fun pictures. What animal could this be? So we look at that, I don't know, maybe it could be a pig. Maybe it could be a cow. I honestly don't have an answer to what animal this could be. So if anyone figures it out, go ahead and send me an email and let me know. But the question is, or the instructions are, draw 2 straight lines that break this large square into 4 smaller rectangles. 2 rectangles should be 1/3 shaded, 1 should be 1/2 shaded, and 1 should be 1/5 shaded. And so I'm going to go ahead, and this is really to show that we have to kind of sometimes approach math by just trial and error, or maybe less trial and error and more like sophisticated trial and error, intelligent guessing. So there's 2 lines. Why not? And if we look here, we have 1, 2, 3, 4, 5, 6 total squares in that bottom right corner, and 3 of them are shaded gray. So that's 3 out of 6, or a half. Oh, that looks promising. We're a little bit on our way. And then this one up here in the top right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4 out of 12, or 1/3. Oh, that's another one. All right, we're getting somewhere. Now let's look at this next one. We have 1, 2, 3, 3, 4, 5, 6, 7. So we have 21 squares, and 3, 4 of them are shaded. Well, that doesn't reduce, and that's not one of our targets. All right, well, that was a solid start. Let's try again. Now I'm kind of feeling good about that bottom right corner, so let's just kind of move this over 1. Here we have 1, 2, 3, 4 shaded out of 9. All right, well, 4 9s doesn't reduce. We haven't gotten any closer. Can I move it up a little bit? So here we have 1, 2, 3, 4, 5, 6 shaded, 1, 2, 3, 4, 5, 6 that aren't. So that's 6/12 or a half. Okay, so that's promising. Now let's look here at the next one above it. So we have 1 set of 3, 2 sets of 3 that are full. So 1, 2, 3, 4, 5 of those. So we have 2/5. Well, that's not one of our targets, so try again. Okay, so we'll try this one. Is that the same one we just did? That's the first one we did. How about that one? So we have 1, 2, 3, 4 times 3 is 12 total. 1, 2, 3, 4, 4/12. Ooh, that's a third. That's promising. So we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 of those clusters of 3. 4 of them are shaded, so that's 4 out of 8. Or if we want to count them, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 24. So we reduce that to a half. Ooh, so we have a third and a half. We're on the right track. 1, 2, 3, 4, 5 columns, and one of them shaded. Ooh, we have a fifth. All right, we better hope that that last one's also a third. So let's see. This is 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5. 6 times 5 is what? 30. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what is 10 out of 30? Oh, thank goodness. It's a third. So a little bit cleaner version of that is this one here. And so when we draw those two straight lines, that top right one is a half, that bottom right one's a third, the bottom left one is a fifth, and the top left is a third, which is exactly what we wanted in the directions. Now I give us this example because this really makes us think about the big idea or the concept of fractions, is that in each one we have some shaded portion. And so instead of saying shaded, we'll be a little bit more general. We have this part that's specified, if I could spell, that almost looked like parrot. We have a part to a whole. And so fractions, the big idea is that there is some part and some whole that always must be specified. Now, we'll come back to fractions in a later video, but this is really just kind of to think about, okay, so there wasn't a set process. I kind of just started by drawing a line, and then I tried moving each of those lines any which way to get to the right answer. Here's another example, but notice the directions have changed. It says draw 3 rectangles so that one is 1/4 shaded, one is 1/5 shaded, and the other is 1/2 shaded. And so this looks like a tree, and that's maybe not up for debate. Maybe you could say it's broccoli. Maybe it could be broccoli or cauliflower. So we'll go ahead and draw a rectangle here. And then I can't draw a rectangle that's just over here in the corner, because if I did that, that would have none shaded, and we're not looking for one that's 0. So instead, we'll go ahead and slide that further over this way. Oh, look at that. And then that's my third rectangle. Now we'll start with that bottom left one, and I'm going to use the column counting process that I used in the last one for one of them. So if one column shaded to 1, 2, 3, 4, 5 total columns, so we have 1/5. And you could count them 1, 2, 3, 4, 5 out of 25, which reduces to 1/5, right? And so use whatever strategy makes the most sense for you. That goes back to then there are many ways that we're smart at math. There are many different ways that we think about mathematics, and it's important that we support each of us in using the strategy that makes the most sense for us. And so here we have another column, 1 to 2, 3, 4 of them, 1/4. So we have our quarter and our fifth. And so now we just need to hope that that top one is half shaded. And you could count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are 18 of them shaded. And there are 4 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 36, which is 1/2. Right? Not too bad. But is there another way that we could see this half? How about, I'll use a different color here. If I think about moving this square over here, and then I think about moving this square over here, Now when I go through, it alternates. White, black, white, black, white, black, white, black, white, black, white, black. Keep going. Remember we moved this one here, so that one's white. Black, white, black, white. This bottom corner one is black now. White, black. This one is white. Black, white, black, white, black. And since we started with white and ended with black, half of them are shaded. Or we could think of it, let me erase some. Another way we could do this is we could look at, there's a pair of two that are half shaded, half un. So what we can do is we can look for these pairs. And as long as we can completely fill this out, all right, and this is where it gets messier. So this one will go here, that one will go with that one with that one, that one with that one. And since we could break that all down into ones that were half shaded, the total's half shaded, and that one, again, works. Right, so there are many different ways that we can see these fractions. So what I'm going to leave you with are a couple more of these to think about. So what is this? My brain always thinks that this is like a crab when I see it, but maybe, I don't know, maybe it's even like, maybe if we turn it, it looks like something different, or maybe it's even upside down. But think about, first off, what is that? If anyone figures it out, let me know, because I'm not sure. But this one is like the tree one. It says, draw 3 rectangles so that one is a third shaded, one is a half shaded, and the other is a quarter shaded. And then here's one that looks like a cat to me. It says, draw 1 straight line. So this is like the first example with the pig or cow, except instead of 2 lines, we're just drawing 1. And we're going to have 2 rectangles at the end. One will be a half shaded and one will be a fifth shaded. And this one will be interesting because notice we have these little triangle pieces, which are half of a square that we're going to have to account for. And then this one, which looks like a dog perhaps, again has the triangular pieces. But like the first one, we're drawing 2 straight lines. It's going to break this into 4 rectangles. And remember, a square is a rectangle, so one of these shapes could be a square. I don't know if it is, but it could be. And after you do that, I want you to reflect. So it's really important that after we do something, particularly something that doesn't look as much like math at the beginning, is think about how we solved that problem. Because math is fundamentally about solving problems involving quantities. So what strategies did you use to solve the puzzle? Did you have a particular process? You were like, oh, I started by just drawing a random line, and then I worked it left to right, or something like that. Did your strategies change as you solved more puzzles? Did you start to find a pattern or some sort of process that worked more often when you had to draw lines? Were some of them more challenging? And why? Were some of them, it just took longer to find an answer? Was it the ones with the triangle pieces, the half squares that were more challenging? And then how did you convince yourself or prove that your solution was correct? Did you just count the shaded squares and put parts to holes? Did you rather use columns? So think back on your work and think, how did you get to these answers? And really, I start with this because I want us to bring in the 8 standards for mathematical practice. And so the Common Core State Standards, which are adopted here in Pennsylvania, and I think last count was like 42 of the 50 states have adopted these standards. There are really 8 big practices that we focus on in mathematics. The first is we make sense of problems and persevere in problem solving. So we figure out what the problem's asking, maybe we put it into our own words, and then we try a way to start, and then if we get stuck, we try again. If we get stuck, we try again, and so we keep going and going and going, and we figure out how it is that we get to our solution. So we make sense of problems and we persevere in problem solving. And then we're able to reason abstractly and quantitatively. And so these 8 standards, which I'm kind of going through now and then we'll retouch on throughout the semester, are instead of content specific, like you need to learn to add multi-digit addition up to 1,000, is regardless of the content we're looking at, we are looking at, right, so regardless of the content we're looking at, what we see is these are the processes that undergird all of the mathematics. And so we can maybe reason abstractly and quantitatively. So that's looking at that picture and then we're able to bring it down into the specific counts. Or maybe we can use numbers and pictures and things to kind of reason. And these, like I said, we're going to touch on as we go throughout the course. Another is constructing viable arguments and critiquing the reasoning of others. So it's important that we're able to explain what it is that we think about in mathematics. And then we also important that we can compare our strategy to someone else's. We can figure out if they're different, why they're different. Because maybe that doesn't mean that one of us is correct and the other is incorrect, but rather just that they're different. We can model with mathematics, and so we're going to talk about like the chip model and the field model and all of these sorts of models for mathematics. And so thinking about what is it that it means for showing the mathematics in addition to the numbers that we're working with. Being able to use appropriate tools, and so maybe that means using a number line or using a calculator or using a model or a balance, right? So being able to pick the tools, because we have a lot of tools in our mathematical toolbox, and being able to pick the right one for the right problem is really important. And then part of it's attending to precision, and so being cautious and careful, making sure that we aren't making mistakes, maybe going back and checking our answer at the end, taking our time as we work through the problems, using mathematical processes properly, are all ways of doing mathematics. Looking for and making use of structure. I think of them, sorry, I tapped too far. This one maybe is the least clear, but maybe it's looking at like 10 plus 7 equals 17 is the same as 7 plus 10. And so seeing patterns that, oh, we can add in either order. Or when we look at a number chart, we're able to see, as I move down the columns in this addition table, it increases by 10. So we have 10, 20, 30, 40, right? And so seeing numbers and shapes and objects and finding patterns and repeated kind of things within them. And then the last standard for mathematical practice is looking for and expressing regularity in repeated reasoning. So this is finding patterns, seeing when calculations are repeated. So here we have this bottom left one of 10 plus 3 equals 13. She sees, oh, well, if I take 2 from that 10 and give it to the 3, or rather, what you would actually do is you would start with 5 plus 8. You would take the 2 from the 5, give it to the 8, and now 10 plus 3, because 10 is easy to work with, we get 13. Or lots of other ways. And so these posters actually come from Bridges, which is a elementary math curriculum, and I like to include them because I think they do a really great job of summarizing mathematics is more than content. It's these particular ways of going about solving mathematics. And so here's another summary slide that just has each of them: persevering in problem solving, reasoning, right? So all 8 of them are here. And I want us to think about these as we're working through the course. When we get to models, which one makes the most sense? Or when we're doing addition and subtraction, how do we attend to precision? What does it mean to look for structure or constructing arguments? Because after we get through this introductory set of videos on problem solving and patterns, we're going to move into logic. And so what does it mean to construct an argument? How do we know if something is true and something else is true? that when we take both of them together, they're true. And so thinking about these standards for mathematical practice. And that is the end of our first video. I'll see you in the next one.